For those of you who are new stations, welcome. This is a very packed spot, so please get cozy. In case you are unaware, Space Rats is Tucson's version of Astronomy on Tap. Thanks for sharing astronomy with you in bars and pubs all around. So thank you for attending. Thank you for showing your interest in astronomy. Our show works. We have two 25-minute talks for you tonight. We will have a 20-minute intermission between those two for you to go and refresh your drinks. And in each of these talks that you're about to see, there will be a trivia question. That is your opportunity to win a little piece of our merch. Speaking of merch, there's a table over there. It's a little miniaturized the whole setup today. There's a table over there for you to purchase merch and to collect merch if you are the trivia question correct answer. We only accept cash, unfortunately, so if you don't have your cash, come back next month and grab some lunch with your cash. We also do accept donations, as that helps keep the show running. So if you are inclined to donate, we thank you very much. I think that's the very quick version of our introduction. So to talk about how exoplanets are stripped of their atmospheres, please give a warm welcome to LPL graduate student Maria Mutz.
Hi everyone. Is this everyone hear me? Okay. Woo, awesome. Yeah. Thank you. Yes, my name is Maria Taylor. I'm a third-year PhD student in the Planetary Sciences Department, advised by Dr. Tommy Koshman. And today I'll be talking about the Great Escape, how exoplanets lose their atmospheres and with it their potential for life. All right, so let's kind of start at the beginning. What is an exoplanet? So exoplanet is short for extrasolar planet, which means that it's a planet that is not orbiting our sun and it's outside of our solar system. So, our sun is a star and we have planets orbiting our sun. And when you look up at the night sky, especially here in Tucson, you see a lot of stars. Turns out there's like hundreds of billions of stars just in our galaxy. And we think that roughly maybe 50 to 70% of these stars also have planets orbiting them. This means that, order of magnitude, there's hundreds of billions of planets in our galaxy. And here are the ones we have discovered so far. So in this plot, every tiny little pink dot is an extrasolar planet that we have discovered orbiting a star other than our sun. There's about 6,000 of them, so we're definitely not close to the billions that are probably out there, but we're making waves. So in this plot, on the vertical axis, we have bigger planets closer to the top, and we have on the horizontal axis, we have energy from the stars, so we have hotter planets towards me. So big hot planets are in the right upper corner, and cold small planets are in the bottom left corner. So we have Earth-sized right about here, and then how much energy we get from the sun right about here. So if we were to put Earth on this plot, it would be there. All right, so we also have about 10 times bigger than Earth and 1,000 times more energy than we get from the sun. So these are much hotter planets. And if we want to put Jupiter on this plot, we can do that too. We see that Jupiter is about 10 times bigger than Earth. It's a big gas giant, and it's colder than Earth because it's further away. It's about 5 times further away from the sun. But you can see from this plot that a lot of the exoplanets that we've discovered are bigger than Earth, and we know that they're gas giant planets, kind of like Saturn or Jupiter, and they're hotter. So lots of planets that we've discovered, mainly due to observational biases. We don't think that this is a real reflection of which exoplanets are most common, but are receiving more energy than our solar system planets are, and they're bigger. So basically, we have all these gas giant exoplanets, and they're receiving more energy than our solar system. So this kind of begs the question, what happens when you heat up a big ball of gas? So what happens to an exoplanet's atmosphere or the gas around it if it's heated up? So basically the question that we're asking here is, all right, so we have the sun and we have Jupiter at its normal distance. What happens if we took Jupiter and we moved it really, really, really close to the sun, like super, super close, it's gonna heat up, like a lot. So we call these, very creatively, we call these planets hot Jupiters, the puffy planets. So this is large gas giants that are inflated due to receiving lots of energy for being so close to the host star. So essentially the molecules and atoms in the atmosphere or the gas in this planet are heated up and start to move away from the planet itself, and in extreme cases can fly away from the planet altogether, and this is a process that we call atmospheric escape. You can kind of think, this is my favorite analogy, you can think about this like a pot of boiling water, where the pot of water is our planet and the burner is the star. So if we have our boiling pot of water super, super close to our heat source, aka the burner, we will have boiling water and we'll have steam flying away from the atmosphere. In tandem, you can think about the planet like this boiling pot of water. We put a ball of gas super, super close to a heat source, and so we get the gases just flying away from the planet altogether. But, you know, if we move our pot of water away from the burner, we're no longer going to have steam flying away from that boiling pot of water. And just like if we have a planet that's further away from its star, we're not going to get these gases being hot and energetic and flying away from the planet. But again, you know, move it close to the burner, move it close to the heat source, we'll have gases flying away. All right, so theoretically, we as physicists know that if you put a giant ball of gas right next to a heat source, that the gas will heat up and start to fly away from the planet. But how do we know, and have we seen this observationally? Spoiler alert, the answer is yes, we have. That's why I have a jar. All right, so one way that we detect exoplanets in the first place is through transits. So from our point of view, the planet is passing in front of the star, and we're observing the star's brightness over time. So as the planet passes in front of the star, we see a dip in brightness. And we'll see this periodically, and that tells us that there's a planet there. This method tells us how big the planet is and how fast it orbits. But in this kind of schematic diagram, we're assuming this planet is kind of just a solid pink opaque dot passing in front of the star. In reality, for the planets that I'm talking about, they have atmospheres. So when the planet has an atmosphere, the light will filter through the atmosphere as well. Some of the light will be blocked, some of the light won't be blocked, and us as scientists can tell what's in the atmosphere based on which light is lit. So to zoom in on the planet, we essentially have the starlight, and it's passing through the atmosphere, and the atmosphere has all different types of atoms and molecules in it, and the atmosphere will essentially leave a fingerprint on the starlight when we observe it. And with our telescopes, we can see what is in the atmosphere. A good analogy for this I like to think about is water clouds on Earth. So if you're standing and the sun is right above you and there's a cloud right above you and you look up, you're not going to visually see any light. Of course, there's light around you and blah, blah, blah. But imagine that the cloud is just blocking all the light. And we know that it blocks visible light because we can't see it. However, if you're like me and you've been outside and it's cloudy, you can still get a sunburn because the clouds are not blocking the UV rays. So it's blocking the visible light, but not the UV harmful rays that cause sunburns. This is a similar concept where specific molecules in the atmosphere will block some types of light, but not other types of light, and that tells us what's in the atmosphere. Okay, so how do we find escaping atmospheres? What's going to be in these escaping atmospheres is the lightest elements, hydrogen and helium mostly. These are the lightest elements, and so they will have the easiest time running away from the planet as compared to heavier elements. And so if we look at the amount of light we see over time, like I showed before, before I showed this kind of boxy looking transit where we're just assuming the planet was just kind of opaque circle passing in front of the star. But if we look at a color where we're seeing this big escaping hydrogen helium cloud, we're going to get a lot more light blocked over time, which tells us that there's a big cloud of helium and hydrogen around the planet, which tells us that there's escape going on. I'd like to mention that we learn a lot about these exoplanets just from observing changes in starlight. We're not really probing the planet itself here, we're only looking at changes in starlight, and I think that's pretty powerful. Okay, so great. We know that theoretically, that when we put a big gas giant really, really close to a host star, its atmosphere, its gas will heat up, get really energetic, and fly away from the planet. And we've seen this observationally by viewing the gases filtering through the atmosphere as the planet passes in front of us. But why do we care? So the first reason is exoplanet habitability. I would be remiss if I didn't put a Star Wars reference up here. But essentially, we think that for life as we know it, you need an atmosphere to support life. It's the first question we ask when we're thinking about habitability. Does the planet have an atmosphere? Does it not? And if it's, undergoing atmospheric escape, it's probably not going to be an environment that any of us want to be around. More specifically, the escape of specific species may hinder habitability. A good example of this is water escape on Venus. So Venus is kind of our twin, our sister planet. It's similar size as Earth, similar mass. It's pretty similar distance from the sun. But it's extremely uninhabitable. If it is hot enough on the surface of Venus to melt lead, so none of us want to go there. And it's thought to have water in its atmosphere in the past, which can cool the atmosphere, but it lost all this water through atmospheric escape, making it, the harsh environment we know it today. Another reason we care is for exoplanet evolution. So like I said, for habitability, the atmospheres may fly away entirely if the escape is really strong, or heavy elements may be left behind. I already mentioned that light elements have the easiest time running away from the planet, so this is things like hydrogen and helium, but other heavier things may be left behind, which also has implications for habitability. So we may start with a planet with an atmosphere, lose it entirely, and just be left with, a rock, essentially. Or we may be left with an atmosphere enriched in heavy stuff, and when I say heavy stuff, I'm basically talking about anything except hydrogen and helium, so water, metals, anything. The third reason we care is for exoplanet demographics. So this is kind of a study of the general population, all the exoplanets that exist. Why are they so big? Why are they small? Why does the population look like that? So I'll bring us back to this plot where, again, each little pink dot on this plot is an exoplanet that we have discovered. And we can start to ask questions about, why are there no planets here? Why is there a blob here? Why is there a blob here? So one thing that we know that atmospheric escape shapes is this kind of hot Neptune desert. So this is where we would expect to see lots of hot Neptune-sized planets, but we don't see that many. And we think that's due to atmospheric escape. And it's kind of hard to see on this plot, but we have a small planet radius valley where we kind of have a dip in planets along this line. And we also think that's due to atmospheric escape. So to zoom in on that a little bit, on this vertical axis here, I'm showing the number of planets. So if you have a taller rectangle, you have more planets. And then on the horizontal axis, I have the size relative to Earth increasing towards me. So we have a good amount of planets near 1.3 Earth radii, and then kind of none here. And then we have, 2 to 3 Earth radii, we have a lot of planets again. So the theory behind this is that, for the smaller planets, they're planets without an atmosphere, and for the bigger planets, they're planets with an atmosphere. And the reason there's kind of no planets in between is because this is where atmospheric escape is working. Okay. Trivia time. I was asked to put a trivia question in here. So my trivia question, I don't know if everybody can see, is what year was the first exoplanet discovered? A, 1808, B, 1959, C, 1992, and D, 2007. So...
Yay.
Correct.
What's the answer?
It was C.
Oh.
Okay, so now I'm going to talk a little bit more about what I do specifically. I model the escaping atmospheres of planets. So I run computer simulations to try to understand these helium and hydrogen signatures in the atmosphere and how we can use that to better understand the structure of escape. So we want to understand how hot these planets are, how fast they're losing mass, and all of this has implications for habitability. So I don't have any really cool pictures of me. Lots of my astronomy people do cool telescope stuff, but this is what I do. Here's me at my desk. My friend Melissa took this photo. So here's me at my desk doing my coding, and then here's me giving a thumbs up because coding is perfect all the time. It's perfect all the time. So this is me in my element at my desk. Okay, so this model includes very detailed physical processes, so we can understand these escaping hydrogen and helium signatures, but it's governed by some very basic physical processes that you may have seen in high school physics class, and even if you haven't, I'm going to explain. All right, so the first is conservation of mass. This is just basically saying that you cannot create or destroy matter from nothing. Conservation of momentum, this is just saying that you cannot create motion out of nothing. You need to have a force or stop motion out of nothing. And conservation of energy, put very simply, this is basically like you can't create heat or cool something down from nothing. So these are very basic physical processes, physical principles that we're using Okay, so the first exoplanet that I ever modeled is the HD 209-45-8b. As you can see, these are very exciting names. We call these the telephone number names because they're just painful to say. This one actually does have a colloquial name. It's called Osiris because we know this planet to have an escaping atmosphere, and Osiris is an Egyptian god who lost his limbs. And so this planet's losing its atmosphere, Osiris lost his limbs, same thing, right? So this planet's kind of famous, actually. This is kind of our archetype, well-studied hot Jupiter. It's the first exoplanet to have a detected atmosphere at all. And so there's lots of research on this planet, so it was kind of a good first topic of study for me. I showed that diagram earlier where we had the sun over here and we had Jupiter over here, and we basically moved it really close to the sun. That's this. That's exactly what the system is, basically. It's around a sun-like star. It's a Jupiter-like planet, Jupiter mass, Jupiter radius, but it's at 5% Earth's orbit. So basically, imagine if we moved Earth 95% closer to the sun. It kind of feels like that here sometimes, but it's I'd also like to mention that this planet is 157 light years away. A light year is the amount of time it takes light to travel 1 year, which is equal to 923 trillion miles away. So this planet is really, really far, but by observing the changes in the starlight due to the planet, we know what the atmosphere is made of, we know it exists in the first place, and we know it has an escaping atmosphere, which I think is really impressive. For the observation people, not what good job guys. Okay, so I wanted to take us back to this slide that I showed earlier on how we know that there's escape. So I'll just explain it again. Basically, we have the planet passing in front of the star, and if we look at the color that either helium or hydrogen blocks, we're probing this big puffy escape cloud, and we can see that escape is actively happening. All right, so here's some real data for HD 209-45-8b. So we can see the amount of light blocked, and we see that there's a big dip right here at the wavelength that helium blocks. So I modeled this planet, and I wanted to try to match this data, and yippee! My model is matching the data. On this planet, I did, first of all, got a model to match the data, which is always good from a theorist point of view. But I also did a case study varying the star a little bit, varying the planet a little bit, and seeing what controls this helium signature, trying to understand the physics behind it. But then I moved on to other planets. So I decided to model two similar types of exoplanets. These are both hot Jupiter exoplanets. They're not all in the same system orbiting the same star. I just put this for comparison. but we have telephone number names HD1A9733B and HD149026B. I'm just gonna call them the purple planet and blue planet and the pink planet because that's more fun and easier. So essentially these planets compared to HD20945AB are archetype of Jupiter. They're similar size, similar radius, similar distance from their star, very, very similar systems, but they all have very different escaping atmosphere signatures. We would expect that with similar mass, radius, distance from their star, that they would have similar escaping signatures, but they're all very different. And so using my model, I wanted to try to investigate why. Alright, so I already showed this very nice pink planet, HD209, with my model matching the data. And next we have the purple planet, and oh, looky here. Telescope data in white with a amount of light blocked, and we have the wavelength that helium blocks, and we have a big dip here, and you see that my model is also matching. And then HD149, the blue planet, we don't have as good telescope data because the helium signal for this planet is really, really small. So instead of some nice data points with some nice error bars, we basically have the telescope saying, the signal shouldn't be larger than this. And oh, looky, my signal's not larger than that. Yay! So my model doesn't exceed this limit. So in summary, my model is reproducing all of these observations. Basically, I've just changed the white points to correspond to the model with the color. The model's overlapping the observations. This is good. So now we can try to explain why they're all so different, even though because they're similar systems, we expect that this dip should be of similar size and shape for all of these planets. And they're matching the observations yet. Okay. So one physical thing that my model has kind of uncovered is that I mentioned before that heavier things have a harder time escaping because they're heavier, lighter things have an easier time running away. It turns out that hydrogen flies away easier because it's lighter than helium, which we didn't expect. We expected that the picture kind of looked something more like this, where we had helium and hydrogen escaping together. Yes, helium is heavier than hydrogen, but not by a lot. And so we thought that the escape was strong enough that they were escaping together. But it turns out that the picture looks this is a cartoon, but it kind of looks more like this, where hydrogen is flying away easier because it's lighter. And this is a new physical process that we have discovered with our model that's operating in these systems. All right, so I'll just talk a little bit about why my research matters. This helps us learn how planets change over time, and this tells us, which planets might lose their atmospheres, which ones might keep them, which is important for habitability. I know I've talked a lot today about these hot Jupiter-like systems, and we know that, a big ball of gas is probably not going to hold life in the first place. But these are the planets where we have the best chance of understanding these processes, and then we can try to understand them better for smaller planets that may have life. This also guides future telescope missions as we search for habitable planets. So I shouted out here the Habitable World Observatory, which is NASA's next flagship or a really big mission. And this program will be specifically looking for habitable worlds. And this builds a foundation for understanding what planets could host life or are habitable. All right, so in summary, this picture, big, puffy, hot Jupiter, sad, Earth, happy, because Earth has us on it, and this hot Jupiter will never have life. So we have discovered around 6,000 planets that orbit stars other than our sun. Due to observational biases mainly, a lot of these planets we've discovered are big, gas, giant bubbles, super, super close to their host star. And these planets, because they're so hot, are likely undergoing a process called atmospheric escape, in which the atmosphere heats up, gets a lot of energy, and flies away from the planet completely. And this process shapes exoplanet evolution, the general shape of the population, and their potential for life. And to get esoteric, by studying these worlds far away, it's really humbling to study these planets and learn how crazy they are, and it makes us think about how rare and resilient our own planet is. So thank you, and I'll take any questions. You do questions?
Yeah.
Okay. I saw your hand first.
So, like a lot of this study has to do with like the transit method we don't see the sun's light coming from the atmosphere, but we can also detect exoplanets using different methods. Is there any way to like also about what those atmospheres are like, or is it hallucinating?
No, yes, I can repeat the question. So the question was that I talked mainly about the transit method, and there's other ways that we can detect exoplanets, including radial velocity, where you basically see the star wiggle because of the planet's gravity, and there's a couple other ways. And are there any implications for those detection methods and what's in the atmosphere? And unfortunately, right now the answer is kind of no. There is a method called direct imaging where literally the planet is big enough and far enough away from the bright light of the star where we literally take a picture of it. It's exactly what it sounds like, where we can get some information about the atmosphere, but transit spectroscopy is what we call it, is really the best way we can probe the atmosphere.
It's like a two-part question. So, is larger planet more likely to keep its helium, hydrogen than a smaller planet if they're the same distance from the star because of gravity and science? And then follow-up is for like a sun-sized star, is there like a safe distance for hydrogen and helium? And are we within that zone?
We are actually losing some hydrogen. I'll let you know. But we're gonna be okay. I swear. To answer your first, repeat the question. The first question was, around a similar star at the same distance, would a big planet be more likely than a small planet to keep its atmosphere? And the answer is yes, because of gravity. A bigger planet will have larger gravity and be more likely to keep its atmosphere. And then the second question was, I don't know.
For a sun-sized star, is there
Safe. It's kind of part of your first question, as it depends on size. Yeah.
but we're not safe.
We are losing hydrogen, but we're going to be okay. Just.
You mentioned, I believe, the Neptune desert, and you looked at the planet graph. So, how well do we think we can sort of reverse and say we think these planets used to have bigger atmospheres than we're in now? Like they have gone through this process.
So, for the hot Neptune desert, we're pretty sure that polar vibration or atmospheric escape is the main player. But I will say for the Radius Valley, there are other models that can reproduce that kind of trend that have to do with where the planets formed as opposed to what happened post-process, like atmospheric escape. So there's some, there's some disagreement there. But if you can guess what my favorite theory is, it's escape.
Sorry, but like if you look at a planet, you think that this planet went through the boiling versus the other one. How would you do it?
I think on a planet by planet basis, I think right now with the amount of data we have, it's hard to tell. We can try to do something with knowing the C to O ratio, which has to do with kind of formation processes, but it's all kind of, we don't have enough good data to tell for specific planets.
Yeah, so you described the atmosphere going away as basically like heat. Is there some other method that like if our atmosphere gets like stripped or blown away, or is it simply just like running off?
There are many other methods. What I talked about today is like hydrodynamic escape because the planet is so hot, but there are other ways that planets have escaping atmospheres. So essentially you can think about, there's another process called Jeans escape that's basically happening everywhere, where particles have a random distribution of, well, not random, a distribution of velocities. And there are some particles that will have really high velocities, not a lot of them, but it'll be higher than the escape velocity of the planet. And so you'll just have kind of some molecules that have really fast velocities just escaping. And there's, a couple other ways that you can get your atmosphere to escape through photochemical processes and things like that. But nothing as catastrophic as what I talked about today, where the atmosphere heats up and flies away in cold. One more question. No more questions. Okay.
Let's make our pick. So, thank you so much, Emma. With that, we shall take our 20-minute intermission. Right now, it is 8 o'clock on the dot. We'll be back here at 8:20. Don't forget to take your bartender. Come on over, grab some lunch from our table. And yeah, see you back here at 20. Zero. I would like to introduce our second speaker, right? Here to talk talk about Hollywood's next big star, the Neutron star. Please welcome from the physics department of the University of Arizona, students of Maria Mutz.
Thank you to everyone who stuck around for my talk. My name is Maria. I'm a PhD student in the physics department and obscured observatory at the University of Arizona. I'll tell you a story about neutron stars, and I also have a bit of Hollywood. Their representation of movies. Let's start. So, origin story. This is me about almost 2 years ago now, giving another space draft. And this one was about the discovery of neutron stars. And as I reflected after giving this talk, I realized two things. One, I stopped at the good part here. Like, I want to know how we discovered them, and then what happens? Are they still relevant? Did we just go, okay, and move on? No, we didn't. They're still super exciting and relevant, but I didn't really get to them. And realized that it was probably important to tell everyone about it, because I went to more space draft talks, and I saw so many black hole movie references. There's a bunch of good black hole movies out there. There's a lot of Interstellar. There's other ones that have come out across the decades. And come on, Disney made a black hole movie back in the late 70s. And it's not just movies either. Film, TV, everywhere. These are all TV shows with one or multiple black hole centric episodes. And they don't just get mentioned. They're like a significant part of the plot. So, black holes clearly getting a lot of love in sci-fi media. Now I went looking for neutron star movies or TV shows. And I found absolutely nothing until about a month ago, when my partner comes and tells me, hey wait, there's been a neutron star in a movie, you need to change your track. Slight spoiler, there is a neutron star in the new Fantastic Four movie. Many of you have seen it. And they told me about it, and from the second they told me about it, I was a little disappointed. So because they told me that the neutron star is used for something called time dilation. Now, time dilation is an effect that will happen around any object with really strong gravity. Which means it could have been a black hole. They just called it a neutron star. Still progress, I'll take it. But I think we could have done more. And on top of that, they didn't think this was fair. They were like, maybe you should actually watch the clip of the neutron star. That is very fair. So I went to try and watch a clip of the scene with the neutron star. And I couldn't find it anywhere. Until finally, in multiple places, I found it under this title. The neutron star in this movie, for some reason, was rendered in graphics incredibly similarly to how black holes are rendered. Functioned so much like a black hole that apparently many people left the theater thinking it was in fact a black hole that they had seen in this movie. And to me, this is not the neutron star representation in media that we deserve. So, I want to explain all the cool things we could be doing with neutron stars in movies and the things we are doing in real life. But before we get there, I should probably make sure you even know what a neutron star is. I've been talking about them for several minutes now. I'll explain. So, neutron stars are one of the few types of ways that stars can end their lives. This is a really oversimplified picture of the stellar life cycle. And there's like 2.5 tracks here. The top one has an average star. It's going to go through a few phases and probably end up as a white dwarf. If it's really massive, it's going to go along this massive star track down here, explode as a supernova probably, and then end up, depending on the mass at the end of its life, and things that happen in the supernova, as either a neutron star or a black hole. So now you know a little bit about how they count, but I didn't actually tell you much about the neutron stars themselves. And before I do, I'm going to make you guess. First trivia of this show. I already got laughter. Anyone, raise your hand if you want to go after it. What are neutron stars made of? Yes, it's here.
B?
protons, neutrons, and electrons. Not wrong, but not right. I saw here next.
D.
D, yes, all of the above. And if you're confused on how they can be made of protons, neutrons, electrons, and also we don't know, stay tuned, we're gonna find out. It's pretty cool. But at minimum, you do know that there are protons, neutrons, and electrons in neutron stars. Because when they go through a supernova, it goes something like this. Over here, we have our massive star. It's reaching the end of its life. It's burned through several elements, and it has this really dense iron core. And it gets to the point where that iron core can't hold up under the force of its own gravity, and it collapses. As it collapses, everything gets squished together, really hard. And this process, called electron capture, happens, where protons and electrons basically get smushed together and form neutrons and something called a neutrino instead. And neutrinos can radiate away pretty easily, most of the time. It's actually a little harder during the supernova. But a lot of them are going to radiate away, and we're going to be left with this hot, puffy, forming proto-neutron star with a lot of neutrons, but critically, we still have protons and electrons. This is not a perfect process that happens to every single proton and electron. It can even go in reverse a little bit. So the neutron and neutrino, if they get trapped there, can go back into a proton and electron. So, in the early form of this star, we definitely have protons, electrons, and neutrons. And then it's going to cool and get even denser and form most of the neutron stars we see today. Some key features of these fully formed neutron stars are that they're really dense. In fact, we call them the densest matter in the universe. And if you're like, what? I thought black holes were denser. Kinda, but we don't really consider them matter. Because what is this matter, probably, that formed them? What's in there anymore? You don't know what's in there. We don't know what happened to it. We can't really be sure what state it's in. And we definitely can't observe anything about them. So, for practical reasons, we call neutron stars the densest matter in the universe. This dense matter, that's all packed together, can spin, and sometimes it spins quite fast. So it can spin up to as fast as about a rotation every millisecond. And they tend to have these really, really big magnetic fields. They range from what I call very big to absolutely bonkers huge. That's 10 to the 12 to 10 to 15 Gauss, if that means anything to you. If it doesn't, this is about 100 billion to 100 trillion times stronger than the magnets on your fridge. And I think it's 10 million to 100 billion times stronger than the magnets in an MRI machine. And if none of those mean anything to you, that kind of makes sense. These are the strongest magnetic fields in the universe. They're not supposed to feel applicable to your everyday life. But that's how strong they are. And they come in a few types. And I'm also going to make you guess about the types. Trivia 2. Which of these is not a type of neutron star, or a category of neutron star? You raise your hand. I see someone in the back.
B.
B. Magnetar. I'm correct. That is a real type of neutron star. Anyone else? Oh, right here.
Yeah, well, I'll guess D this time.
D this time. They are not all real types of neutron stars, but I love the enthusiasm. Let's go over here.
C.
C. Yes. Quasars. Quasar is actually a type of black hole. I'm going to talk about this.
No way.
So, we have a few categories of neutron star. The first one is pulsars. This is the first type of neutron star that we discovered. It's the most common to discover. Because these are basically the lighthouses of space. They have these beams of electromagnetic radiation that you can see over here, and those sweep in and out of the view of Earth. And this can happen pretty often because they can spin up to once a millisecond. And so as that sweeps in and out of our field of view, we see pulsing signal from them. And that's why they're called pulsars. So they're easy to spot. We don't even have the most data on them. That doesn't mean they're actually the most common type. It's just they're really easy to find once you know what you're looking for. And because they pulse at these regular intervals, they make excellent clocks. It's going to become really important. Another type is magnetars. They are real, and it's our word for neutron stars with super extra crazy magnetic fields. Those are the absolutely bonkers huge ones, okay? It might seem silly that we gave them a different name, but it's not silly, because as these magnetic field shrinks, we actually see new physics, things that star wouldn't be possible with less strong magnetic fields. And so that's why we gave them their own category. Some things about these is that sometimes they're also pulsars. Nothing's stopping a pulsar from having a very strong magnetic field. But even if they're not, sometimes you can see them because they're prone to other electromagnetic flares and bursts that we see. And help us identify them as magnetars. And finally, we have binary neutron stars. These can be in a binary with another neutron star. If they are, they might be inspiraling towards a merger, and they might be creating gravitational waves that we can detect in detectors we built on Earth. And we detected at least one or two of these events happening. We're hoping for many more. But neutron stars cannot only be in binaries with other neutron stars. They can also be in a binary with a white dwarf or a regular star. If they are, instead of merging with that companion, they might slowly eat their companion. We call that process accretion. And there are also sometimes pulsars. There's nothing stopping a pulsar from being in a binary, and sometimes they are. So these are not exclusive categories. They just are useful categories for neutron stars. And with this in mind, okay, these all seem pretty cool. Are they moving with? I'm here to tell you, absolutely yes. What's the first reason? Neutron stars are necessary to human life. Yes, all human life, your life. Because we are all made from stardust. You might have heard this from a friend, a prominent scientist or astronomer, or my personal favorite source of astronomical information, Joni Mitchell albums. All equally accurate and correct. We are made from stardust. But dust from which stars is the question you should be asking. This is a periodic table coded by exactly which star or astronomical event is responsible for producing most of that element. So you'll see that the light elements, way up at the top, can be synthesized in the Big Bang. After that, we have various stars and their disk helping spread these elements throughout the universe. We get up to white dwarf-related phenomena and supernova, and then finally, as we get into these really heavy elements down here, you'll see that the processes required to generate many of these elements, the neutron capture processes, are not easy to come by. In fact, you might think of them like two of the densest objects in the entire universe crashing into each other at high speed to create such an element, and that's exactly what we believe is happening. Obviously, there's some uncertainties in this. We're not actually 100% sure on all of these, but we think that anything with this merging neutron star icon is being created primarily by neutron star mergers. And this includes a lot of important elements. For instance, silver, gold, and platinum. Not just expensive and shiny, but useful for a large variety of purposes. There is a reason that we value them so highly. And even with that, I would not call them necessary to human life. So I'm going to let the Space Drafts team decide whether this is a trivia question. But can anyone tell me which of these elements that have a merging neutron star as their main source is necessary to human life? Yes.
Iodine?
Yes, it's iodine. Iodine is absolutely critical for your thyroid function and really your whole body. You don't want to mess with the thyroid. It's going to mess everything else up too. And it's primarily created by merging neutron stars. So you have multiple neutron stars to thank for your body functioning. Neutron stars. Tell us now. Stars also contain the mysteries of ultradense matter. Maybe this is not surprising because, as I said, they're the densest in the entire universe. And that means we can't study matter at these densities out loud. It's just not possible to recreate that in a lab on Earth or anywhere that we have access to. So, to work on it, we also tried creating a bunch of theories, doing a bunch of calculations about how it should behave. That didn't work out either. Our computers weren't good enough. Our theories are just not there yet. So we have ideas about how matter might behave in neutron stars, but there's a lot of open questions. So on the outside, on the crust, it's almost like regular matter, just really, really dense, but there's still atoms. As we get further in, everything squishes together, and the atoms don't really have space to stay together as atoms. So it just becomes a bunch of particles. You have your protons, neutrons, and electrons all just floating around in a really dense quantum fluid. I like to call it a quantum soup. And then as you get even further, we really have no idea what that is, because maybe those particles break down into quarks, but maybe they don't. Maybe they become something called hyperons, which are normal particles, but heavier. There's a lot of ideas of what could be going on in the core. And in fact, there's even a lot of ideas of what might happen at a lot of the boundaries of where these things take place. So, you might have heard that black holes can do a fun thing called spaghettification. They take matter, and if they're at a certain point near a black hole, they're going to stretch and squeeze it with their gravity and the forces around the black hole into something that looks kind of like spaghetti. It's long, stringy, maybe a little wiggly. So you might be wondering, can neutron stars also produce spaghetti out of matter? And I'm here to tell you, neutron stars might not only contain spaghetti, but in the ocean, anti-spaghetti colloquially, known by some as nicotine, and anti-nicotine. These are just some of the phases that might be occurring in the matter inside the neutron star as all the nuclear and gravitational forces squish them into strange new things, and as they interact with each other. In fact, we even go beyond pasta phases in neutron stars. We might have Swiss cheese or waffles. You can see up here we've got a spaghetti phase, and then we've got a Swiss cheese phase over here. And there might even be superfluids and superconducting vortices. So you can think of those like crazy whirlpool with special magnetic properties. And this is just some of the stuff that might be going on. The only way we're going to find out is by studying neutron stars more. So we already tried all the other ways, and it didn't work. So, you might be thinking though, well that's cool. Sorry, that didn't smell. Alright. You might be thinking, well if this only happens inside neutron stars, and it's the only way to learn about it, probably also only applies to neutron stars. And that's only half true. This physics is relevant to the inside of neutron stars, yes, but it can also tell us about other times in the history of our universe. So this is a schematic of the history of the universe. On the left, we have the Big Bang. On the right, we have right now, us, in this spaceship. And you might have heard of a cool new telescope called JWST, and how it's looking further back at earlier galaxies than we've ever seen before. It's pretty cool. JWST is looking at galaxies right around this era of the history of our universe. So like a little 200 million years after the Big Bang. But the matter inside neutron stars is most relevant to a way earlier era, before particles may have even been forming, or just after, when we're looking at those densities where the universe is so dense that it can't form those particles yet, or maybe it does, maybe it goes through some other crazy phases that we haven't named yet. And we're definitely not building a telescope that can look back there anytime soon. So this is another thing that they can reveal to us. But this is not where neutron stars' relation to the early universe ends. They have many other ways of teaching us about it, including through gravitational waves. So I'm guessing with the spacecraft crowd, at least some of you have heard of gravitational waves and detectors like LAMDA before. In case you haven't, gravitational waves are basically ripples in space-time. And we built these crazy cool machines to detect them. One of them is called LIGO, and it basically works like this. You have these two giant laser arms, and as a gravitational wave passes through the system, it's going to stretch and squeeze the space-time between those arms, which is going to cause the lasers to interfere with each other and create a signal that tells us, hey, a gravitational wave just passed through here. This is one way that you can detect gravitational waves, but it's not the only way. We could also just use pulsars. So I mentioned that they're excellent clocks. So instead of waiting for lasers to interfere with each other, we can take the signals from two pulsars and compare when we think we should see a pulse from when we do see a pulse. And that change in time, we're going to assume, is being caused by gravitational waves passing through the space-time between the pulsar and Earth, stretching and squeezing it, just like we stretch and squeeze the arms of the LIGO. And then we can say, yeah, we can look at the correlation between those two and use the pulsar to Earth signals just like arms and gravitational wave detector. But we have a few key advantages with pulsars. One, we're not limited to however many arms we can build. We already have thousands, because there are thousands of pulsars out there already. And they're spread out, and we have a lot more angular resolution here too. Like we can look at how this one is correlated to this one, and how this one goes with this one, and learn a lot more, potentially, about those gravitational waves. The other advantage of the pulsar system is its scale. So, like you can only play so low frequency of a note on an instrument, depending on how big it is, you're going to need a really big gravitational wave detector to detect a really low frequency of gravitational wave. LIGO, the one we're currently using, the gravitational wave detector based with lasers, has arms that are about 4 kilometers long. And for the next generation, we're going to build one that gets launched into space, and it's going to have arms that are 2.5 million kilometers long. So, huge upgrade. Pulsar arms, in a pulsar timing array, are about 500 to 50 million light years long. I put the number of kilometers up here in case they mean something to you, but they're a lot bigger, right? And that means that we can detect more low frequency gravitational waves. So if we look here, we have frequencies of gravitational waves with very low ones starting on the left and very high frequencies starting on the right. Now up here in purple, we have all the possible sources of gravitational waves. And down here, we have all the possible detectors. So LIGO, the one we're currently using, is a terrestrial interferometer. It's going to get some compact inspirals and mergers like we've already seen, and has the potential to get some pulsars and supernovas as well. If we launch them into space like we're hoping to, we can get our space-based detectors to get more of those, and a little bit of these supermassive black hole binary mergers, which are black holes that are really big at the heart of galaxies, basically entire galaxies a long time ago merging, and their signals slowly reaching us today. And early universe stuff, more stuff from the Big Bang, which could be stretching a large part of this, but basically to get into those low frequencies, we're going to need something like the pulsar timing arrays, and in fact, we've already started using these to detect signals from the early universe. We found like a background of really old signals that have come from all over the universe and are currently sloshing around near us. And now we're trying to pinpoint individual signals more and do other cool stuff. So I would just like to point out that pulsars, aka neutron stars, are the only object that appears in both the source and detector section of this plot. Pulse couldn't. And this is not the only technology that pulsars can enable, because excellent clocks are really important and valuable, especially in space. So, to have any sort of navigation system like our current GPS, you need really precise calculations of time. That's because satellites, which inform our GPS, are moving really, really fast. And they have to constantly do a calculation of where am I based on how fast I'm moving? Where are you? How fast are you moving? And they do all these calculations, and if their time is even a little bit off, they're going to tell you you're somewhere else. It's not going to work. You're going to get lost really fast. So they need really good clocks. And we have really good clocks. We have some excellent clocks on there. Like this. This is one of our best clocks. It's at NIST. It's called the cesium fountain clock. And this can totally keep time well enough to do these calculations. But critically, I don't have a great picture for scale, but it's about the size of a refrigerator. It's got a lot of delicate parts. We're not hurling this up into space and attaching it to satellites. That would not work out well. And so, for GPS and for spaceships, we need to actually recalibrate the clocks aboard them regularly in order to prevent them from drifting and basically everything failing to work. So, final trivia question. How often do you think atomic clocks in space need to be recalibrated from Earth in order to keep working correctly? Back here?
Say twice a day.
Yes! Woo! Twice a day! So that means if you get out of communication with Earth for even a little bit, not very long, suddenly you are lost forever in the depths of space. Not a good scenario to be in. And to deal with this problem, NASA has been developing a new navigation system using pulsars to recalibrate the clocks. Because pulsars are conveniently spread out all over the galaxy and beyond. further than ever before, and do it all without getting lost. So this is honestly like already a step of sci-fi, but it's actually happening right now. Also, I think it's a really cool full circle because, you know, humans started out navigating by the stars, and then we developed all our other really cool technologies. And now we're back to navigating by the stars. Specifically, the neutron stars. Navigate by a black hole. And now I know what you're thinking. One, yes, neutron stars really are so great. But two, oh my gosh, this person made an entire talk to complain about neutron stars in movies and rag on black holes. I promise you, I'm not just a complainer, okay? I'm a problem solver. And I have a few neutron star movie premises to pitch to you right now. I think they're gonna be great. I think someone's gonna hop on them really soon. The first one was Ian. Journey to the center of neutron star. The travelers encounter new pasta phases, sail on superfluids, avoid the dangerous vortices, discover long-lost, strange new physics at the heart. And, you know, maybe we get to it now. Also, if there can be dinosaurs and waterfalls beneath the Earth's crust, I think this movie is going to be equally fun and definitely more scientifically accurate than the Earth version. If Interstellar and debates about the ending have taught us anything, it's that some people really care about scientific accuracy. Alright, next one. Raiders of the Lost Ark. I like to imagine this is like a far future dystopia where we've like overrun all of our families and you only get them if you're really elite. And so our adventurers are risking their lives on a mission to obtain their allies from the ejecta of a binary neutron star merger. And a killer, for those who I should have explained before about 20 seconds ago, is the longest lasting signal that we see after a binary neutron star merger. And it's actually a signature that those elements that we talked about are being formed. So in this movie, they must dodge the gamma ray burst, which is a short, very high energy burst that comes after some neutron star mergers. They need to surf the gravitational waves, track down the ejecta they're looking for. They don't all look the same. And compete with other scavengers and space pirates along the way. Instant hate. I'm telling you. Finally, my favorite neutron star movie premise, Operation Glitch. This is a half-star movie where a team tries to avert an interstellar war by tampering with the neutron star navigation networks. I like to imagine that first they're just trying to like hack the computers at headquarters, where our headquarters may be. But when that doesn't work, they have to hack the neutron stars themselves. Because I can tell you this, there's a lot of things that can mess with neutron stars. We don't even know all of them. Sometimes they do glitch, and we don't know what's going on. But maybe they need to find a companion star, it needs to add some mass, no, not too much, don't much clouds and form a black hole. Black holes do get mentioned in neutron star movies. Maybe they need to bring out some really crazy magnets. I think this is going to be so much fun, and I can't wait to see it in action. So, you these, hopefully some movie producers in the audience have some questions, or requests for movie rights or consultation. Thank you so much for listening to my rants. Yes, question.
Do we know why they spin so fast?
Ooh, the question is, do we know why they spin so fast? Maybe? Maybe probably yes. I'm working on this right now, actually. So, I mean, for one thing, if you have an object that's spinning, when it's still a big star about to die and exploding, and then it goes through the whole explosion and it's getting shrunken down, just the conservation of momentum alone can increase that spin rate. But is that enough? Some say yes, some say no. Some think it has to do with other processes that happen during the supernova, or maybe other processes that happened in the history of the neutron star's life. So it could be that it didn't start out spinning as fast, but it did have a companion, it's already done eating it, and it accrued a lot of mass and angular momentum from that companion, and now it's just all spun out. Or it went through a merger earlier. Maybe it was a two-way door. not long ago, and now we have a neutron star. There's a lot of different channels for explaining exactly how they spin and how fast they are. Yes, back here, then here.
What is the jet that comes off of a pulsar, and why is it misaligned with the spin axis?
Great question. So there's a lot of different potential. Oh, sorry. Question was, what is the jet that comes off the pulsar, and why isn't it aligned with the spin axis? So in very early pulsar models, it was aligned with the spin axis, but that obviously made no sense because if it's aligned with the spin axis, we're not going to see the pulses, and nothing makes sense. And now we have lots of different ideas about how the magnetic fields might help form those jets, and all the particles around the neutron star as well might be contributing to them. It might not even be that there's really like one explanation, because the light from neutron stars goes basically over the entire like electromagnetic spectrum. There are radio pulsars, there are optical pulsars, there are X-ray pulsars. And so it's possible that, the mechanism that explains light from the radio pulsar is not the same one that explains light from the X-ray pulsar. The short answer is complicated magnetic field related things, and beyond that, it really depends who you ask. And it's an active field of research. Alright, so here's next.
So from a scientific perspective, what's your favorite pulsar?
Oh man, so I'm a theorist. For my favorite pulsar and why. So the answer is not going to be as profound maybe as like someone who actually looks at them. I just simulate them. My favorite pulsar is my like imaginary one on my computer. I have a favorite. I like the crown pulsar. Which I like it for its history because the crab pulsar is inside the Crown Nebula, and we have this whole system for trying to deduce about how old pulsar is, or a neutron star, and in this case we were able to compare that against actual data because we found actual records in Chinese text and really text all over, like I don't want to say ancient, well, it's not really ancient, but text from around the 1500s documenting that they could actually see this supernova from Earth, which is, difficult for that to just happen. Oh, there's just a supernova that you can see right from Earth. And it's so well documented across like multiple cultures, and especially the Chinese texts are some of the best ones, and so they're famous for it. But I don't know, I think it's really cool that we actually went back and like found astronomers hundreds and hundreds of years ago documenting this for us, and now we can like compare our theory to their observations. Yeah. There we go.
Is there like a critical angle where you can or cannot detect the pulsar based on where the jets are pointing?
The question is there a critical angle where you can or cannot detect the pulsar based on where those beams of light are pointing? Yes. But like it depends for every different pulsar, because I don't know, how bright are they? How far away is it? How good are our telescopes? How wide an angle is the beam? Like there's a lot of modeling and theory that's going to go into exactly for each pulsar when we wouldn't be able to see them, but we assume there must be some out there that are just sweeping around their light in a way that's never making it to Earth. Yeah. Alright, I'm going to go back here and then over here again.
What sets the beam size for a pulsar?
What sets the beam size for a pulsar? Depends who you ask and what type of radiation they believe is like the mechanism for creating the beam, and what they think is happening there. But there are like relativistic effects that happen, because the trouble with observing light from pulsars is that they have such strong gravity that they're constantly lensing their own emissions. And so it's not as simple. So the gravity, they're actually bending the light around them as it leaves them. And so you can't just model, oh, it creates the light and then it travels over here to us. It creates the light does some wonky stuff around the neutron star because it's got such a strong magnetic field, and then it's making it to us. And so teasing out exactly what is the light being created and how it's created and where versus how it's actually traveling to us and what's happening near the neutron star is a thing I used to work on in my research. I think we had someone over here again?
Yeah. we see any neutron stars or pulsars outside?
Outside the Milky Way?
Correct.
Well, again, really exposing my Earth nature, but I think, yeah. I think so. Because we have them in our galaxy. I think we have them, yeah. To also, like, see them in what sense, right? Like I said, there's so many different types of pulsar signals or neutron star signals you can have. So, like, what wavelength or type of radiation are you seeing them, right?
What about the PTAs?
The pulsar timing arrays?
Yeah.
Oh gosh, I feel so unprepared for all these practical questions now. I
think they're all galactic.
They're all galactic? Okay, yeah. I believe that. They're all galactic. Thank you, Meredith.
The peer reviewed.
Alright, so they're mostly Milky Way. The ones that we're using for the pulsar time. Obviously, there are pulsars probably beyond Milky Way. That would be very weird. We would probably start an internal. They're probably happening here. I see someone going on.
Last question.
Last question.
Okay, perfect. I just wanted to mention that the first exoplanet discovered in 1992 that I mentioned in my trivia question was discovered around the pulsar. So, big pulsar.
Also, I mentioned optical pulsars. The first optical pulsar was discovered for. See, here's somewhere. Pulsar.
Yeah.
Thank you so much, Maria. Alright, so that wraps up Space Drafts number 111. We will be back here on December 17th for Space Drafts 112. For our trivia answers, and grab your little bit of merch. Yeah, now we'll just about to it. Thank you all so much for coming. We'll be back here, December 17th, 7:30 p.m. See you all then.